The first question is, find the Laplace transforms of the set of time functions that are given here. A, t squared e to the power of minus at ut. B, t plus 2 whole squared times u of t minus 1. So this time function really starts at t equals 1 onwards. The third function, time multiplied e to the power of minus at, t e to the power of minus at multiplied by u of t minus t, a delayed step function. So once again, this function starts from t equals capital T onwards. It's truncated for values of t less than capital T. D, e to the power of minus 5t times hyperbolic cosine cos 3t ut. We have not talked about Laplace transforms of hyperbolic functions, but you can always express them as the sum of exponential functions and then combine this with e to the power of minus 5t and you can find the Laplace transform of that. D, e, t e to the power of minus t sin t ut. Here again you have a combination of these factors. We have worked out examples where e to the power of minus t sin t, we found the Laplace transform, but that multiplied by t. So whenever you multiply by t, it's equivalent to taking the derivative in the transform domain. So you have to use those properties to find the Laplace transform of this. F, given that f of t has the Laplace transform of f of s, what would be the Laplace transform of another function derived from f of t in this manner, e to the power of minus bt times f of t minus b. So it's scaled by a factor b. In addition, you have multiplied it by an exponential term, e to the power of minus bt ut. Take b to be a positive number and then find this out, find the Laplace transform of this in terms of b and f of s. Then we are given the waveforms of two time functions. One is an aperiodic function. This is all the function there is for outside this range from t equals 1 second to 4 seconds it is 0. So within this interval t equals 1 to 4 it behaves in this manner. It linearly rises from 0 to 3 units and then climbs down to minus 2 steeply and then remains at minus 2 from 2 seconds to 3 seconds and then once again comes back to 0 at 4 and stays there for t greater than 4. So it is an aperiodic function described in this manner. H is a periodic function. The variation for one period 0 to t naught is prescribed as here. It starts from a and comes down to 0.8k in half a period linearly and then it jumps to minus 0.2a at this point and again increases linearly and reaches 0 at t equals t naught. So this is the basic variation in one period and find the Laplace transform of this variation in one period and then use the property of Laplace transforms for periodic functions to find out the Laplace transform of the entire time function. As a second example, we have listed here a set of Laplace transforms. Find the time functions to which they correspond. That means find the inverse Laplace transforms of A, s plus 2 over s squared plus 8s plus 15. B, s plus 1 over s plus 2 whole squared times s plus 3. That means there is a repeated pole here. So you have to use the rule for finding out the residues when repeated poles are involved. C, 2s squared plus s plus 1 over s times s plus 2. You observe here that the numerator has the same degree as the denominator. Therefore, apart from the factor which correspond to k1 over s plus k2 over s plus 2, you also have a constant term 2 which is the ratio of the two leading coefficients. So 2 plus some k1 over s plus k2 over s plus 2 is the partial fraction expansion of this. So corresponding for the 2, the inverse Laplace transform will be 2 delta t. So whenever the numerator degree happens to be the same as the denominator degree, you have a constant term in the partial fraction expansion and in the inverse Laplace transform you have a delta function. D, you have 4s plus 5 over s squared plus 2s plus 10. These lead to complex conjugate poles. So instead of finding out the residues of each of the complex conjugate poles, you can do it. That is one way of doing this. Other way would be to treat this as s plus a whole squared plus omega squared and then try to find out the inverse Laplace transform in terms of cosine and sine functions with an exponentially decaying amplitude. Then you have 2s plus 1 over s plus 2 times s squared plus 1 whole squared. Here you have repeated poles on the imaginary axis, slightly more complicated, but you can handle this in the same way as you have done earlier. Then f s plus 2 over s squared plus 8s plus 15 times 1 minus e to the power of minus 4s. In tackling this problem, you already know the inverse Laplace transform of s plus 2 over s squared plus 8s plus 15. So all you have to do is use this information here, because e to the power of minus 4s means whatever f of t you had obtained here is the same f of t delayed by 4 seconds is what corresponds to this. Therefore, use this information that you already obtained here to find out the f of t corresponding to this. 1 over s, 1 plus e to the power of minus s. So if you had 1 minus e to the power of minus ts, we recognize this to be the Laplace transform of periodic function of time. So all you have to do is multiply both the numerator and denominator by 1 minus e to the power of minus s. So you have 1 minus s, 1 times 1 minus e to the power of minus s by s times 1 minus e to the power of minus 2s. Therefore, you can recognize this to be the Laplace transform of some periodic function, with the Laplace transform for the basic period being 1 minus e to the power of minus s over s. You can find that out. Similarly, here you have e to the power of minus pi s by s squared plus 1 e to the power of minus pi s minus 1. So if you multiply both sides, numerator and denominator, by minus 1, you have 1 minus e to the power of minus pi s. So you can remove that, then find out the Laplace transform of the remaining function, and once you introduce that, it becomes the Laplace transform of periodic function of time. So using all the properties that we have derived, you find the inverse Laplace transforms of all these 8 functions of S. Question number 3, you have a capacitor in a circuit, current I is the current passing the capacitor, and Vc of t is the voltage across the capacitor. Suppose to the solution of this network we found out the Laplace transform of the voltage across the capacitor Vc of s. Let it be in symbolic form a1s plus a0 over s cubed, a1s plus a0 over s cubed plus b2s squared plus b1s plus b0. That is the Laplace transform of the voltage across the capacitor. Now, using this information in terms of a and b constants, find the final value of the capacitor voltage Vc infinity. B, the initial value of the capacitor voltage, which is Vc 0 plus immediately after t equals 0. Also find out the initial value of the current I 0 plus. And lastly, find the initial value of the derivative of the current I prime 0 plus. This means this is di by dt evaluated at t equals 0 plus. So this is an application of the initial value theorem, final value theorem, and the derivative rule. All these are needed for solution of this problem. In other words, you don't have to explicitly find Vc of t. Using this initial value theorem, final value theorem, and the derivative rule, you should be able to find out all these quantities in terms of the a constants and the b constants. Question number 4, use convolution theorem to find the inverse Laplace transform of 1 over s plus 1 times s plus 2. Verify using the partial fraction expansion. So this Laplace transformation can be thought of as the product of 1 over s plus 1 times 1 over s plus 2. You can find out the time functions corresponding to these two factors, and since it is the product that is involved in the transform domain, in the time domain it is a convolution. So it is a convolution of the time functions corresponding to 1 over s plus 1 and 1 over s plus 2. Find out the corresponding time function. Now you can also find out the inverse Laplace transform using partial fraction expansion, verify using partial fraction expansion, and compare the two answers. Both of them must naturally agree. So this is an exercise in not only partial fraction expansion but also using the property of convolution. Question number 5, you are given two time functions. F of t is a pulse which lasts from 0 to 2 seconds having an amplitude 1, and g of t is an exponentially decaying time function e to the power of minus tt ut. find ft star gt, that is the convolution of ft and gt. Both are causal time functions, both are amenable to Laplace transformation. Find this down in time domain, purely working out in time domain from the basic definition of the convolution integral, you find out ft star gt in time domain. As an alternative, verify using Laplace transform. In the second step, what you have to do is find the Laplace transform of f of t, find the Laplace transform of g of t. Since we are interested in the convolution of these two, that whatever is the result of this convolution must have for its Laplace transform f of s times g of s. So you find the Laplace transform of this, find the Laplace transform of this, both are simple to find out. Find the inverse Laplace transform, you get ft star gt. Lastly, you have the error Et of a controlled quantity in a control system has for its Laplace transform this expression E of s equals s plus 1 over s plus 1 whole squared plus 4. The error Et of a controlled quantity in a control system has for its Laplace transformation E of s plus 1 over s plus 1 whole squared plus 4. Without explicitly finding E of t, you don't have to find the inverse Laplace transformation of this to find E of t. Without explicitly doing that, evaluate E infinity, that the final value of this error. B, integral 0 to infinity of Et dt, the integral of that error over the period 0 to infinity. C, 0 to infinity t et dt, that is time multiplied t et dt. This you should be able to do it without actually finding out E of t using initial value theorem, the rule for integration, and so on and so forth. You can also extend this to ask you to find, I can ask you to find out integral 0 to infinity of E squared t dt, that is the integral of the square error, but that requires a convolution in the complex domain. Since we have not discussed that, we have not included that type of question. So this exercise covers the various properties of Laplace transformation that we discussed in the earlier 6 lectures. In the next lecture, we will discuss the application of the Laplace transformation technique to evaluation of transients in networks and systems.